Today, I will explain new verification methodologies to detect the functional corner case bug. For that, we use methodologies of the ISO 26262. Let's start. At the first, we will introduce ISO 26262 functional safety standard, and we will explain why we use methodologies of ISO 26262. For a long time, electronics were a comfort feature, like PC or our mobile phone. If went something wrong, they shows only the blue screen or reset itself. Even we can losing our progress or our data, but there is no critical hazard will not happen. But now they are safety features. As you see, the ADAS or some kind of sudden acceleration or the unintended malfunction of airbag or something features can be happened, and it can threaten our human body. To prevent this hazard on the road vehicles, ISO 26262 was published on the 2011. So this functional safety standard describes the all possible hazard and how to avoid or control this hazard to save the life of human. This ISO 26262 is very similar with the previous functional safety standard named IEC 61508. Both IEC 61508 and ISO 26262 are risk-based safety standard. That means aim to address possible hazard and to prevent or control that hazard on the system. And the importance of semiconductors emphasized recently. So in 2018, the ISO 26262 has added Part 11 that includes guidelines for semiconductor applications. This picture shows the overall framework of ISO 26262, and this diagram is known as V diagram because their flow sequence is like V from like concept and architecturing and hardware development with software development, and also mass productions. Guideline also included in this diagram and this standard. So I have very impressive about this diagram and the structure of ISO 26262 because they are described their requirements from the vocabulary and their concept and documentation and how to develop and how to we verify it. So you can see that many things hazard analysis and risk assessment flow is and safety analysis flow is located each step of each development phase. That is very key point of this functional safety standard, and we can know that this review and assessment and analysis is a key point, and their purpose of make this functional safety standard. So for that, we have to know what is functional safety. ISO 26262 defined functional safety as avoidance of systematic fault and control of systematic fault conditions and control of random hardware faults. So this is for the assurance of functional safety. We have to the control and or avoidance of this kind of fault. In previous slide, we shows that purpose of functional safety is avoid or control the two kind of failures. One is this random hardware failures, and another is systematic failures. The random hardware failures is predictable during each lifetime, so it means that we cannot detect in our development process, and when we using this device about the 5 years or 10 years, its characteristic can be changed due to the external the stimulus or something else. So we have to make a safety mechanism to control these kind of failures, and we have to predict the possibility to occur this kind of failures. For that, the single point fault metric SPFM and latent fault metric LFM was introduced in ISO 26262, and each age level, automotive safety integrity level, required some the threshold of for this metric, and how can this device can detect that the possible the failures. It shows with the diagnostic coverage, and from these informations we can get some named of failure rates, and based on these informations we can have a PMHF for each age level. Based on this information, we can make FMEDA, and make assurance for each functional safety for random hardware failures. Another one is systematic failures. Systematic failure is caused by human error or some kind of mistake or some kind of the development process. So this is one of the target of our functional verifications, and typically we call it about bugs. How to prevent these systematic failures? This is same purpose of our design verification field, and ISO 26262 relies on the traditional design verification methodologies for prevent these systematic failures. It means that there is no the ISO 26262 does not provide any new methodology or some kind of new recommendations not included in there. But as system complexity increases, so our SOC include multiple controller, and multiple cores are located in each block, and each controller will generate each function with its own scenarios. So it means that unintended action can occur the, the, during the interaction during their work function. So it makes so complex the unintended the hazard case can be occurred in our design. And it is very hard to detect through our traditional verification methodologies. And nowadays, this kind of hazard or systematic failures are found in the product level silicon. To detect this kind of complex systematic fault, we need another new and robust methodologies to detect them. I will introduce the example of this kind of complex systematic failure cases. This shows the error notice from the IP provider. That is a kind of CPU cluster and their coherent interconnector. So when the CPU cluster changes their state transitions, like power down or wake up, that times this cluster generate the syscall request to the interconnector to blocking or connecting its current network. And the interconnector also responds with the syscall X signal. But this error shows that when syscall request was happened, but syscall X is not responding to situations, if Sunil transition will come into the CPU cluster, the CPU cluster will go to the hang state, like a deadlock, and it cannot working anymore. Like these situations, it is very hard to detect our traditional verification methodologies because we cannot detect this T1 and T2 sequence on our verification the environment, and we have to generate between T1 and T2. So until now it only depends on the randomized test, and our the slow simulation environment cannot reproduce that conditions on the pre-silicon level. So type of these errors were the detected in the silicon level testing, and it makes some kind of additional the cost for its mask revision. Another example shows the protocol conflict cases between PCIe and the ACE interface. So PCIe and the ACE interface has its own protocol and its the ordering rules. So this picture shows the three conditions for each requirement for this for conflict. When the PCI-RC buffer has been overflowed, its read and write channel will be blocked, stalled. And in this situation, the condition 2, the CPU will generate write-back transactions. These write-back transactions cannot issue from outside the cluster, and at the same time, the condition 3, the PCI will generate posted write, and this posted write will generate with write line unit transaction, and it will generate the make invalid SNOOP to the CPU cluster. But the pending write-back transaction will block this snooze transaction, and this posted write cannot be completed. The PCI RC buffer cannot proceed anymore. So these three conditions will happen at the same time. This deadlock chain is the made, and the system will fall into the deadlock. For generally reproducing this kind of deadlock, we have to make these three conditions at the same time. So until now, it is almost impossible in our verification environment, and this is concerning with the three block like CPU and current interconnector and the PCIe. So it is very hard to verify the former or another methodologies. So our purpose of this presentation is to find a way and find the possible failure cases on our design in pre-silicon level. For prevent this type of systematic failures, we made new methodologies that named of systematic failure analysis. The purpose of SFA is to expand the functional coverage by extracting risk factor from the IP level and predicting the risks. For this, we made the process that is failure mode definitions and risk assessment and FMEA and DFA. This methodology is already used on the ISO 26262 for another purpose, but the risk prediction, the methodology is also useful for our functional verifications. Let's see the failure mode definition. Failure mode is possible failures that can occur in our design, and we have divided into the 5 type of failure mode. The first FM1 to FM3 is very fundamental functionality and very basic test verification process for our traditional methodologies. And from FM4 and FM5 is some kind of stress cases or some complex scenarios, because FM4 is state transition issues. So we know that in our experience, every state transition condition has many unintended the bug was happened. So for that reason, in case of state transition cases, we have mixed FM1 to FM3 like basic functionality with the state transitions, and we verified its corner case and found the failure mode. And FM5 is about independence between each separated function blocks. So until now, the verification unit is a function block, and there is the lack of effort, or the owner is not assigned for the interfunctionality. So regarding FM5 is research the failure cases in case of functionality interactions between the 2 or 3 owner blocks. Another one is risk factors. Risk factor means in our system design, there has many the possible, the critical section is the inside which functionality or its blocks. So the first hazardous functionalities means that like state transition cases for power down or clock gating or power gating or reset. Like this, state transition will be the hazardous functionality, and in our experience, the specific functionality was the bug was found in previous our project. We make found that hazardous functionalities was in there. We will uh, make a weight on the risk factors. And also proven in use is if our target block has same IP with our project, that already has proven the functional the integrity in our project productions. And the severity level also shows that if some the hazard case was happened, we can check its effect to the IP or its block or its whole system will how serious the effect was propagated into our SOC architecture. And another thing is about known issues in another project. If some issue, if specific issue was happened in another project, it's it also the it can be also happened in this project, and we have to check and verify that issues on our current project because our the integration or the design engineers the, can uh, have the mistake, same mistake on our project. So last one is applicable workaround. Workaround means that if this block was found in the critical hazard issues or systematic failures in silicon level, the backup block or backup IP is located in our the SOC. It can the it can replace with the failure occurred IP. And also our software team also check its applicable workaround in the review session. Through this risk factor assessment, we can get a point for each risk factor, and through this the sum of these points, we can get the risk level point. So according to each point, we can define the SFSL, that is the systematic failure severity level, and this is similar with the ASIL, the automotive, the safety integrity level, but the SFSL represent the serious of when this failure happened. That it means that we have a higher priority for our verification the process. Through these informations, we can make FMEA, the failure mode and effect analysis table like this shown in the picture. So FMEA is actually not for our design verification, but the FMEA also very useful for predicting the failure and its effect to the system level. As you see, we defined all functionality and find some possible the failures with the failure mode definition, and we assessment is the SFSL to shows its severity when it happened. So based on this FMEA table, we can make various the verification and we can make the complex scenario for the verify the corner case conditions. The final process of SFA is DFA. DFA is dependent failure analysis. Through this DFA, we can verify the specific one fault, whether it can cause another failures or it makes the mixed with another failures with generate new failures should not be occurred. This is the requirement of independence of freedom from interference. So we can find these kind of dependencies with each block and each failures. The purpose of DFA is find DFI. DFI is dependent failure initiator and coupling factors. Coupling factor is the functionality that will propagate the specific fault to the another failures. For that, we adopt the fault injection features. This fault injection is different with for the random hardware failure. We use this fault injection by our backdoor interface of our test bench environment. Using these fault injections, we are injected the ECC error injection and the MMU, the translation fault generation, and using the last feature that implemented from ARM V8 architectures, it can generate the internal CPU, the error cases to CPU or interrupt controller and the system MMU. Through this fault injection, we can make the condition of like a random hardware fault was occurred or some kind of a bit flip or the failure occurred conditions. And another thing is to make the coupling factors. We are using the functionalities that mainly the interaction with the different block and the different IPs. First one was first sharing coherence access, and this will generate so many the transactions regarding the coherence channel and the Snoop. And also the DVM, distributed the virtual memory transaction broadcasting, also will be the coupling factor for complex stress environment. And also the exclusive access for spin lock and the CPU close power down also can be the coupling factor of the power down and on, like our previous first example of functional corner case. From this slide, we introduce the output of DFA. First one is fault tolerance report that was made our own the methodologies, and it shows that previous coupling factors is generated as stimulus 1, 2, 3, 4, 5. So the purpose of this one is for each generated error, these kind of coupling factors can be generated on other failures or not. These scenarios was generated by the PSS tools, and each stimulus and coupling factor will be made by each PSS action, and PSS tool will generate the randomized and the make sequence using this kind of coupling factors. And we check that even though this coupling factor was generated and the fault has been occurred, we can recover from that failures, and we also make the column for fault tolerance time interval information for our software team. Using previous FTR reports, finally, like this table, we can get the DFA result from our process. So it shows that FMEA ID also in one column, and the DFA element and redundant element was described in here, and the functionality and the DFI information also the written each columns. Through this DFA result, we can verify and check the dependencies with each block and each functionality and each failures. Until now, we've introduced the way to find the possible failures cases on our system, and how to find and how to verify is not introduced yet. So after we find the possible failure scenarios and the scenario conditions, we have to verify it, but as the previous example of complex corner cases, so the problem is it is very hard to reproducing on our verification environment. For that, we have made the systematic failure models using the PSS and the machine learning algorithm. We will introduce how to make it and how to verify and reproduce each complex conditions of functional corner case. As you see the picture below, so when we execute its function in different CPU, they're running at the same time. So our expectation is each functionality will be occurred at the same time. But in hardware view, the output hardware event will occur with a different time, because the internal processing time is different for each IP. For the reasons, we have modified each delay to the CPU 0 and CPU 2, and actually at the finally we can make each hardware event occurred at the same time. So, but this delay assertion need many the tuning and the change each delay. How many delays is required is very difficult problem, and need many effort to change each values and check the result so many times. For that reason, we have made this test bench structure for systematic failure models. So I will explain each modules of these failure models. First one is the generated test from PSS that shows orange color box, and that is a software program, and that automatically generated from PSS tool. And as you see, we can uh, the configure its delay value with PSS input, and this PSS input will generate with the PSS delay functions. So the PSS tool will generate the various delay, the value, and easily make a scenario for each CPU. As you see, the generated software code, inside this PSS delay will send the mailbox to the outside the external delay counter. So delay counter is functionality for the assurance for the cycle, the resolution, the delay time, because we did not using the CPU timer or some kind of features for the delay feature that they made make using the software, because it can change it. It cannot assure the exact time in the cycle resolution, and the, its minimum the time unit is a few microseconds. But we need the nanosec or clock cycle levels resolution is needed to synchronize each hardware event. For that reason, we have made the system verilog environment the UVM delay counter that the wait delay specific clock, and that will generate interrupt to the CPU. For we have to fix the time consuming to assurance its linearity. And the next one is output monitor. Output monitor is a functionality to check the target condition was happened or not. So target condition is action A and action B output hardware event will occur at the same time. If output monitor detects that signal was happened at the same time, it will report through the log file, log print about its scenario name and seed number and the direction and the PSS input delay and the simulation timestamp informations. And this reported output data was gathering into the output repository, as you see in the bottom block. Gathering information in the output repository that shows in the one, that will be the extract to the form of coordinate, like number 2. So each actions will the coordinate made from input delay and its output timestamp informations. Using multiple disk coordinate, we can make linear equations like number 3. So we to get the linear equation for action A and action B, like number 3. So this linear equation can the present like the number 4 graph. Please note that our purpose is find the delay value that has the same timestamp value. So for that reason, we can make the 5 equations that is form of Diopanton's equations, and using this equation, we need to find each solution for A and B that satisfies these equations. This equation is, we can get the solution for this equation through the extended Euclidean algorithms. So through this algorithm, you can get the combinations, multiple combination of the solution for A and B, like 6. So this is our machine learning implementation flow, and at the 3, in the extracted linear equations, we can apply the linear regression algorithm of machine learning, and we can gathering we make the different input delay, and we can search, and we expected that the expected timestamp value for delay A and B. So that informations in the linear environment, we can predict which delay will make the common timestamp value. That is the usage of machine learning algorithm, and it was very simple, but very useful. This diagram shows the flow of the machine learning based the failure models, the learning sequence. As you see, the first step is setup sequence, and the setup is we select the PSS test scenario that shows the specified action A and action B, and after that we gathering the sample regarding input delay and simulation timestamp informations. And after that, learning stages, we will find the regularity for the gathering data from the gathering data, and we will generate the linear equations, and based on that linear equation, we will move to the analysis flow, and in the analysis flow, we can the proceeding the extended Euclidean algorithm, and we will find the common simulation timestamp value that occurred at the same time for multiple hardware events. So in the analysis stages, the very important thing is need to check is linearity about this gathering data. If there is any the linearity rule was broken, these analysis stages will set this range again and return back to the gathering stage, and we will start gathering the learning data again. So through this flow, finally we can get the proper delay value for multiple actions, and using that scenario, we can reproduce the complex functional corner case failures for the verification and detect that failures. So until now, we are introduced about the SFA and the systematic failure model generations flow, and now these SFA output materials can be reused for the various purposes, for the various safety requirement standard like ISO 26262 or IEC 61508. As I said in previous slide, the ISO 26262 is rely on for the systematic failure avoidance depends on our traditional design verification methodologies. It means that our design verifications, the results can be used for their safety standard. So for that reasons, our current the verification activity it will be uh, very valuable to using the another purpose. But their format and their requirement is very difficult, and their requirement need more uh, detailed review and analysis flow is needed. For that, SFA will be very helpful to satisfy that requirement for the requirement-driven verifications. This is the final slide for our presentation. Recently, higher levels of reliability will be required for semiconductors. For this, we have to reinforce the hazard analysis and risk assessment for the predicting the risk and our design integrities should be analyzed. This is not only the verification issues, it is required whole teams, design and architecture and verification, and its software team also need the effort for the reinforcement of this process. And also in the design verification field, we have the innovative expansion of the functional coverage is needed. So until now, like previous the corner case, the examples, we cannot detect like previous the corner case conditions. So we need to make new methodologies and new the thinking of its coverage is needed for our design verifications. That is not improved only with the EDA environment. We need make more effort for developing the methodologies. In these presentations and in these studies, we are using and mentioned about methodologies of ISO 26262, but the purpose of this is not for reference. In the futures, the requirements for our semiconductor and its verification quality will be the common like ISO 26262 requirements. For that, we need to improvement and adopt new the methodologies for expanding our verification coverage. Thanks for watching my presentations. If you have any questions, please feel free to contact me. Thank you.